Hello, my name is Aurelio Garcia Ribeiro. I am a Senior Director of Product Management for the Java Platform Group at Oracle. I have been with the team since before the launch of JDK 7, and one of the best parts of my job is that I get to present what is new in each JDK version, not only to other Oracle teams, but specifically to developers and end users. Today, I will give you an overview of the largest changes in JDK 17. If you saw the keynote, you will recognize some of the slides, but we will go into more detail during this session. Before we start, some housekeeping announcement. The session will last 30 minutes. We won't have time for a deep dive into each of these changes. My goal is to give you a summary to help you decide which features you want to learn more about. There are other sessions that will cover some of these changes in more detail, and you can always read the JEPs in OpenJDK. Although most of the sessions are the same in the 2 dates, there are a few sessions that are unique to each date and that expand on some of the JEPs that I will cover. For example, for the agenda on September 14, we have Nikolai Parlog diving into pattern matching, while on September 16, Paul Sandoz will expand on the Vector API. It will be worth your time to review the recordings for both dates. Don't wait until the end of the session to ask questions. We will be answering questions in real time during the session using the Q&A widget. With that out of the way, let's dive in. JDK 17 is the second release of 2021, the 9th release since we switched to a semi-annual release cadence, and the second long-term support release. Users of JDK 16, and for the matter 15 through 12 if they haven't upgraded yet, should move up to JDK 17. The next set of critical patch updates, scheduled for mid-October, will only include updates for the LTS releases 17, 11, 8, and 7. There are no further updates for JDK 16 planned. JDK 17, being an LTS, will continue receiving updates even after the release of JDK 18. JDK 17 will receive updates at least for 8 years until September of 2029. JDK 17 delivers 14 JEPs, which stand for JDK Enhancement Proposals, the unit of work that we use to specify the largest changes to the platform. I've grouped them into 6 categories. We have 2 changes to the Java language, one of them in preview mode. In the libraries, we have 5 JEPs, 3 changes to the standard, and 2 in incubator module. 2 changes will make it more likely that code written today will continue working in the same in future versions of the JDK. And as with prior versions, we deprecate and remove functionality as needed. JDK 17 introduces support for a new platform, and we deliver some changes to the OpenJDK codebase. First, we will go into the language features. These changes will be visible to most developers, and they're the most fun to show. JDK 17 adds sealed classes. They were introduced as preview in JDK 15 and came back for a second preview with 16. Sealed classes and interfaces restrict which other classes or interfaces may extend or implement them. In Java, a class hierarchy enables the reuse of code via inheritance, but sometimes it can be used to model the various possibilities that exist in a domain, like the kinds of shapes supported by a graphic library. When the class hierarchy is used in this way, restricting the set of subclasses can streamline the modeling. What we really need is a superclass to be widely accessible, but not widely extensible. Here's an example. A class is sealed by applying the seal modifier to its declaration. Then, after any extends and implements clauses, the permits clause specifies the classes that are permitted to extend the sealed class. A sealed class then imposes 3 constraints on all the permitted subclasses. The sealed class and its permitted subclasses must belong to the same module, or if declared in an unnamed module, the same package. Every permitted subclass must directly extend the sealed class, and every permitted subclass must choose a modifier to describe how it continues the sealing. It could be final and allow no more subclassing. It could in turn be sealed, which means it will have its own set of permitted subclasses. Or it could be non-sealed. A sealed class cannot prevent its permitted subclasses from doing this. One and only one of the modifiers must be used by each permitted subclass. Java lang class will get 2 new methods, so that code using reflection will be able to determine if a class or interface is sealed, and if so, to get a list of the permitted subclasses. JDK 17 adds, as a preview feature, pattern matching for switch expressions and statements. Being a preview means this change is not yet permanent, and use it will require a command line argument at compile and at runtime. More importantly, being in preview means that there is still a small window to provide feedback and improve the feature before it gets finalized. Preview features are not beta, they're fully specified and documented. Now that we have releases every 6 months, we can afford to ask for feedback on features before we burn them into the language. If you would like to weigh in on this feature, you should use the discussion list for Project Amber in OpenJDK. Pattern matching for switch allows expressions to be tested against patterns. Current switch statement works on few types: numeric, enums, and strings. If we wanted to use patterns to check for a certain number of possibilities, we would use a chain of if-else statements. Using pattern matching in a switch expression, we can make this clearer. A bonus point is that this code is optimizable by the compiler. Remember that the case statement has to be exhaustive, so in most cases you want to add a default value. But there's one thing missing here. Traditionally, switch statements and switch expressions throw a null pointer exception if the select expression evaluates to null. Testing for null is done outside of the switch statement. But now that case labels will allow type patterns, it would be better to integrate the null into the switch statement. This makes the code easier to read and to maintain. After a successful pattern match, we often need further tests, which can lead to cumbersome code like this. We could improve readability if the pattern supported a combination of pattern and Boolean expressions. So, guarded patterns allows us to write this in a clearer way. The first case matches the strings of length 1, and all the other strings are caught by the second case. There are a couple of new gotchas that arise with pattern matching for switch. The first one is that a pattern could dominate later patterns. It is possible to have an expression match multiple labels in a switch block. This is allowed, but they must be placed in the right order. Here we have code very similar to what I just showed for guarded patterns, but with the order of the case statements reversed. Since the first label will catch all strings, including those of length 1, the second label is never reached. It is dominated by an early case. This will result in a compile time error. Another new possible error is to have a fall through when declaring a pattern variable. In this example, if the variable was a character, it would print character. But then, as there is no break statement, execution would flow to the next case label. Since the variable I declared in the second pattern would not have been initialized, we will get an error. It is therefore a compile time error to allow flow through a case that declares a pattern. Falling through a label that doesn't declare a pattern is fine. Changes to the library can either provide new functionality or improve existing APIs. With JDK 17, we bring in a few new APIs. JDK 17 refactors some of the code used to generate pseudo-random number. Earlier versions of the JDK included several classes of pseudo-random number generators, but they didn't have a common interface, which made it hard to replace one class with another one. This JEP introduces several new interfaces, including random number generator, which all the existing PRNG classes now implement, as well as other classes that extend random number generator with more specialized capabilities. Random number algorithms change relatively frequently, so it's not a good idea to request one by name. It is possible that an algorithm you ask for will not exist in a future version of the JDK if a better one supersedes it. Instead, we now include a random generator factory that can be used to get a stream of all available algorithms, which can then be filtered by their properties. One could filter for implementations that are splittable, jumpable, and have more than a certain number of state bits. The code could then select any of the current algorithms with those characteristics. With the release of macOS 10.14 in 2018, Apple announced its intention to move away from OpenGL APIs in favor of a new rendering pipeline with better performance called Metal. The Java 2D APIs used for Mac rely on the OpenGL APIs. It does have a software rendering option, so it could manage without them, but the performance is better using a specific platform-specific APIs. Now, in JDK 17, the default pipeline remains OpenGL, but the system will now fall back to metal if OpenGL fails, as we expect it will if Apple removes support for OpenGL. You can also specify that you should use the new pipeline. If you run Java on a macOS, we'd like to ask you to try this and report any issues to the OpenJDK Lanai mailing list. We hope to be able to switch to the new pipeline by default before Apple stops shipping with OpenGL. Deserializing untrusted data is an inherently dangerous activity. The key to minimizing deserialization attacks is to prevent instances of arbitrary classes from being deserialized. JDK 9 introduced deserialization filters to make it possible for developers to specify which classes can be deserialized. You can create an allow list or a deny list or a combination of both. This was considered such a valuable feature that the functionality was even backported to JDK 8. The problem, though, is that until JDK 17, using deserialization filters requires every stream creator to set the filter, or for the use of a single static JVM-wide filter. These restrictions make it hard to use deserialization filters when using third-party libraries without making those filters too inclusive or too restrictive. JEP 4.15 introduces a configurable JVM-wide filter factory that allows for creating per-stream filters. This allows for dynamic and context-specific filters, so we no longer require the participation of every stream creator. We're looking into backporting this functionality into earlier releases. We also get to test two APIs, courtesy of Project Panama, that will make it simpler to run non-Java code, for now specifically C libraries on x64 and ARM64 platforms. Although Java has supported native method calls using Java native interface since Java 1.1, this has always been hard and brittle. Using JNI requires developing and maintaining multiple artifacts like a Java API, a C header file, and a C implementation, and this must be done for each supported platform, making the effort platform dependent and require different tool chains on each platform. Other frameworks and tools have appeared over the years that improve on JNI, but they're all still less than ideal. Project Panama aims at making it trivial for Java developers to use any native library. These APIs remain for now in an incubator module, which is morally equivalent to a preview feature. The biggest difference between preview and incubator is that we use previews for language features and JVM changes, and incubator modules for APIs. Both JDK 16 and 17 offer, again in incubator module, a vector API that will give developers a way of expressing computations that will reliably translate at runtime to vector hardware instructions on supported CPU architectures. The JVM supports auto-vectorization of some operations, but it relies on some known patterns to identify when it can convert to vector operations. Giving developers the means to directly write code with vectors in mind will yield more consistent results. Vector operations enable more work to be performed in a single CPU cycle, and this can lead to significant performance gains. Now, the majority of developers will not have to do this directly. We expect that library developers will take advantage of this API to optimize common libraries that most developers rely on. Once that happens, most developers will experience significant performance improvements just by adopting those updated versions. Here's a conceptual example. If the same operation will be executed on a group of values, it might be possible to load those values into vectors and execute the operations on the complete set. In this example, rather than needing 4 multiplications, 4 additions, and 4 assignments, we can get to the same result using SIMD instructions for 1 multiplication, 1 addition, and 1 assignment. Operations that might benefit from the vector API are common in machine learning and in cryptography. Moving a platform forward is not only about adding new features. It is also about making sure that programs behave correctly and are not doing anything that will make it harder to uptake future versions of Java. One of the contracts between the maintainers of the Java platform and the developers that use it is that there is a set of APIs that developers are welcome to use and which future versions of the JDK are likely to continue having. To deliver those APIs, the maintainers of the platform use internal APIs meant to be used only within the platform. These internal APIs are subject to change without notice, and therefore any program that relies on them might break when applying any update. Until JDK 9, internal APIs were not documented in the list of standard APIs, but since developers have access to the source code, they're easy to find. Although there are warnings when compiling with those APIs, some developers still rely on them. Even if you are not calling them directly, there were many common tools and frameworks that use them, so for many years, most, if not all, non-trivial applications relied on them. With JDK 9 and the introduction of Jigsaw, we gained the ability to enforce that only JDK internal code should access those internal APIs. But turning that on by default on JDK 9 would have made it so that all those libraries and frameworks would have stopped working with little notice. Instead, we chose to only add more explicit warnings with 9, and we said we would wait a prudent amount of time before we started enforcing encapsulation. 4 years later, a prudent amount of time has already passed. With JDK 16, we went from still accessible, but with warnings by default, to no longer accessible by default. But it was still possible to relax encapsulation of all packages with a single command line option. With JDK 17, the single command option is gone. So if you insist in using internal APIs, you will have to open specific packages one by one with the add opens command line option. Now that most libraries and developers will not be using internal APIs though, we are probably going to be more willing to change internal APIs with less warning. So please do not use them. There was an unfortunate interaction between the floating point coprocessor instructions used on early x86 systems and the Java language and JVM semantics, making it so that Java had to manage a large overhead of instructions to deliver floating point operations. Matching result in the absence of overflow and underflow could be achieved much more efficiently, but that required relaxing the Java floating point semantics, which is what was done with Java 1.2 as an implementation option. Around 2001, processors started offering new extensions that would allow the more strict floating point semantics without all of that additional overhead. We are therefore now going back to string floating point semantics as the only option. This is unlikely to affect existing applications, as having strict execution was always an option in the runtime. Deprecations and removals deliver short-term pain in exchange for long-term gain and are necessary to allow us to continue updating the platform at a reasonable pace. JDK 17 brings 2 deprecations with 4 removal. Features deprecated with 4 removal will work on JDK 17 for the whole lifetime of the release, but they will be removed in some later version of the JDK. The first one is APIs that were used mostly to support applets. They have been deprecated since JDK 9, but were not yet tagged as 4 removal. Adding 4 removal means that additional warnings will be triggered when compiling code that uses these classes and interfaces. The second one is the Security Manager, which has been available since JDK 1, and which was used to create the Java sandbox where untrusted applets were meant to run. Although the Security Manager in theory could have been used to help protect server-side code, in the real world it was rarely used for this purpose. To use it as intended, it requires developers to adopt a permissions model that is quite brittle and difficult to understand and maintain, and a serious performance penalty. All of these has resulted in very low adoption for securing applications, and many of those are not coded correctly, so they don't provide the security that developers intended to get. The cost of maintaining the security manager is quite high, as it must be tightly woven into all Java class libraries, which imposes an unacceptable tax on future development of the platform. Although it has not been widely adopted for security, there are other use cases for which the security manager has been adopted. Some frameworks use it to keep managed code from calling system exit, or to gain insight into whether an application opens connections to ports or files. These use cases can be addressed by much cheaper alternatives. One of the goals of deprecating the security manager is to help us identify if there are any other use cases that we might have missed, so that we can find or add alternatives before the security manager is removed from the platform. It is too early yet to tell when these features will be removed from the platform. As with prior deprecations, we will consider feedback to decide when most users have had enough time to move to alternatives before the features are removed. Even if we remove them before the next LTS, you can continue using them with JDK 17 at least until the year 2029. JDK 17 no longer includes RMI activation, which was deprecated for removal since JDK 15. Now don't worry, the rest of RMI remains unaffected. JDK 17 also adds support for a new platform. Apple's new computers have been migrated to use ARM64 processors. Adding support for macOS on ARM64 complements the addition of Linux on ARM64 that we did a few releases ago. Although it is possible to run macOS x64 builds on an ARM64 system using Mac's built-in Rosetta 2 translator, that translation did not have the same performance qualities that we would expect on a Java runtime. Finally, not all of the work done in the JDK release shows up directly in the binaries we release. JEPs are also used to deliver improvements or code changes in the OpenJDK projects. Changes like these are only visible to developers working in the JDK code itself. The experimental ahead-of-time compiler and just-in-time compiler were not features included in the platform, but were an experimental set of features that was considered for inclusion around the release of JDK 9. They have seen very little adoption since then, and the cost of maintaining them is not small. These features, being optional, were already excluded from Oracle's builds of JDK 16. So, in that sense, if you were using JDK 16, there's no change from JDK 17. This JEP just removes the source code from OpenJDK. It's worth noting that part of the work to add the experimental JIT was to include an experimental Java level JVM compiler interface. We're removing the experimental JIT, but the JIT compiler interface is unaffected by this removal. Now for some more details about the release, you can right now download JDK 17 from the Oracle Java download page. If you're interested in OpenJDK work, or if you want to preview JDK 18 early access builds, or grab a hold of one of the early access builds for some of the other projects being worked on in OpenJDK, you should visit jdk.java.net. The list of supported platforms is what you would expect. It's the current versions of most common operating systems. It's the same platforms that we supported in earlier JDK versions, revved to the most current releases. The only thing that is new here is what I mentioned before, the addition of macOS ARM64 that we mentioned before. If you want to learn more about any of these JEPs, you should visit the JDK 17 page in openjdk.java.net. Each of the JEPs has a full page with the information that I have covered, many more examples, and technical details. There is also information on which email aliases to review if you care to see the process and considerations that went into many of the choices made. Also, for the features that are in preview or incubator, you will find links to the email aliases where you can deliver feedback that might help us improve those capabilities before they get added to the standard. I hope you found this presentation useful and that you start enjoying the benefits of JDK 17 pretty soon. Thank you.